Greetings everyone and welcome back to the John Audio Tech Show. Today we're going to take a look at an op amp. I have this little test jig board I made up and it's populated with one of these dual type op amps. It's a NJM 4556 or just 4556. This op amp is interesting to me because it features something that your other typical op amps like the NE5532 or the TL072 or the 4562 don't have. And it is high current output capability. It can output 2 or 3 times the current that those chips can output, and that can be useful in some situations. I've seen the chip used to drive headphones. It has enough current to drive some types of headphones, not all. And that can make a very simple headphone amplifier, for example. I'm kind of curious as to its distortion performance. If it's not that good, it doesn't make sense to use it. Well, you remember, if you watch my channel, you might remember a while back I tested the output swing of various op amps under different load resistances right here. And you can see when we got to 100 ohms, the other op amps output voltage swing really collapsed, while the 4556 did much better. So yeah, I want to see how the distortion performance is with this chip, because if it's good enough, I might be able to use it in some simple amplifier circuits. I could use it to drive the outputs directly, say with a lower power amplifier, something that runs on 12 volts, for example. So what are some of the standout features of the chip? Like I said, it has a higher output drive current. It's rated at 70 milliamps drive current, whereas the other ones, they'll be rated only like 25, maybe up to 40. But this chip, like I say, can do 70 milliamps. Has a nice wide supply voltage range from plus or minus 2 volts to plus or minus 18 volts, or just 4 to 36 volts, single supply. Of course, it comes in a through-hole 8-pin dual inline package, so that's handy. And they're inexpensive. They're only 97 cents when I looked at DigiKey for a quantity of 1. Of course, if you buy 10 of them, you start getting a price break there. Now you can find higher performance, high current op amps, but they're going to cost more. So, this is what I would call your jelly bean type component. It's fairly common. It's been out for a while, and it's probably going to hang in there for quite a while. It's not something I would think would disappear overnight. Okay, so what I did is I made this little jig on this perf board, and I have a socketed op amp here, the 4556, and you see next to the socket is another row of sockets. That allows me to plug in different feedback resistors, or connect different components to allow me to test the op amp in different ways. So yeah, it's just a basic board. I got a ground encircling it here, bypass close to the chip, and some wires here. I can interface it using the breadboard here to the signal sources and everything. Yeah, it'd be nice if I enclosed it, but it's just how much effort you want to get into here. I think this will work good enough for a test jig. So what I want to do here is bring power in. It'll go through these capacitors into the supply lines here. Of course, we have our input and the output. I'm going to test it with different load resistances to check the distortion to see how it performs. So what I'm going to use is a 1 kilo ohm resistor in one test and a 150 ohm resistor, because that's what it says on the data sheet, that it can handle 150 ohm loads. Okay, the power supply is on. I'm running it at plus and minus 15 volts. Start off with the 1 kilo ohm load. So I'm sending the signal in with my music player, adjusted it so it's just right before clipping. And this is the attenuator. It's these metal film resistors configured to reduce the level that goes into the computer because the output swing would be very high for that. Also has two protection diodes just in case I screw something up. It prevents the computer's input from seeing too much of a voltage. Okay, so I'm using my computer's audio and this Artist software to take the measurements. And I talked about this in the last video. But when I plugged my music player directly into the computer and measured its distortion level, I was getting 0.003. So now this is the op amp with the 1K resistor load, 1 kilohertz signal, and we're getting this 0.004 something. It jumps around. So that's excellent. Very impressive. Now these nodes, as you remember, they could be introduced by the music player or the computer's audio. I don't know where, but they're pretty low, and that's obvious here since we're barely over the baseline. So this signal is around 8 volts RMS. So let me retake the measurement at a lower signal level. Okay, so now we're measuring the output signal level at 350 millivolts. And when I say output level, that's what's coming out of the amplifier, not what's coming out of the attenuator. And I have to reset the attenuator because I need to get as much signal into the computer. I need to use as much bits for measuring the amplitude as I can to get the lowest possible distortion measurement. If I didn't do that, I'd be getting an invalid reading. The noise went up a little bit, but look at this, still very low distortion. Very good. So now I'm looking at intermodulation distortion, and I'm using two tones, one at 18 and one at 19 kilohertz right here, you can see. And you can see the little sideband nodes, and we have a little node down here at 1 kilohertz. And the baseline should be low as well, 0.003, but it's a little bit higher here, 0.048. I mean, that's not bad, but not as good as what we saw when I measured some other equipment in the other tests, like the JAT 501 power amplifier was doing much better, if I recall. But still, it's not bad. Like I always say, I'm testing at the higher frequencies using the intermodulation test because I can see how the amplifier is performing, because a solid state device will have higher distortion at the higher frequencies. And even though it's not shown on the graph, it is seeing up to 24 kilohertz, so it's seeing the side bands on the upper side as well. So it's counting those in the test. Okay, if I didn't mention, the previous intermodulation test was at the high signal level, and this is now at the low signal level, which is down around 350 millivolts. And it's performing really, really well down there. 0.006 or something like that. It's jumping around, but see, the nodes are pretty much cleared up. No real side bands anymore. Much better. Okay, so what I'll do next is put in the 150 ohm resistor, and we'll see what kind of measurements we get. That'll be the true test because we're pushing the op amp to deliver more current. Okay, so we're back to our 1 kilohertz signal. Now we're measuring at the high level with the 150 ohm resistor. And now you can see distortion has perked up quite a bit. 0.04. If you remember, before it was 0.004, so we're an order of magnitude higher. So yeah, loading that down does lift the distortion levels a bit. Let me try turning down the potentiometer just a bit more, because we're close to clipping. It might, have more distortion in that case because we're really pushing the amp close to its current limiting. So let me turn it down just a bit. Okay, so I turned it down from 8 volts RMS down to about 6.2 volts RMS, and look at the improvement down to 0.01. Well, we're not as low as we were before, but of course, a lot higher current. So this is still pretty good. Okay, so now we're at the low signal level, which again is around 350 millivolts. Again with the 150 ohm load. Signal level is very low, or I should say the distortion is very low, 0.004 something, jumps around. It's even lower than when I measured with the 1K, but I think that is because I just have it dialed in better. It's very touchy to dial that in. I need a 10-turn trimmer or something like that, but at such a low signal level, even with 150 ohms, the current's very low, so that's why you're seeing the distortion, about the same as it was with the 1K load. So, it's not unexpected. Okay, so now we're at the high signal level, 150 ohm load, intermodulation distortion test. And 0.061, again it's set up close to clipping with the higher current, so we'll see more distortion. So let me dial that back just a little bit to see what it looks like. Okay, I dialed back the signal just a little bit, and of course the distortion improved. 0.04 we'll say. It's not bad, I can't really complain. Now let's do the low signal level. Okay, this is the low signal level, 350 millivolts, 150 ohm load. Of course, we're not driving a whole bunch of current, so the distortion is much improved, down around 0.005. Okay, so that concludes the test of the 4556 dual op amp. Pretty happy with the numbers I saw. It may not be as good as the other chips like the NE5532 or the LM4562, but those can't handle that kind of current. So I was kind of concerned that I would see it go above 0.1%, but it didn't, even with the intermodulation distortion test at higher frequencies. Like I say, solid state type amplifier circuits are going to have more distortion at higher frequencies. So that's why I do the intermodulation distortion test using the 18 and 19 kilohertz signals. I can't do a total harmonic distortion test at those frequencies due to the limitations of my equipment, which I mentioned in a previous video, so I just use the intermodulation distortion test instead. So that's good. I think that'll allow me to use this chip in some circuits I plan on playing with here, or creating whatever in the future. So there you have it. Thanks for watching. Uh-oh, he heard the bag rattling. Oh, there's the ingredient. No, yeah, he wants food. You're not getting any Snickers. You don't like this stuff anyway. I put it in your bowl and you'll turn your head up at it. Crude protein, that's 37%, 32%, I can't read.